Good morning, everyone. Glad to be here in Amsterdam. And thank you for coming to my talk. This talk is about blockchain security. And instead of focusing on the application in the upper level, today I will uncover a vulnerability related to the underlying infrastructure of blockchain, which is a Euro memory corruption bug in the node server. The vulnerability can lead to a remote command execution on the node server, and furthermore, a subversion of the whole blockchain. Okay, my name is Haoyu. I'm a security researcher at Tencent Security Xuanwu Lab. I enjoy blockchain and application security, and I was a CTF player at T-Deliverers. Okay, so the first thing is, what is XRP? XRP means XRP Rate Protector. It's a bug killer that has killed an 8-year-old bug, which could lead to a full takeover of the entire ledger. And if you don't know what XRP is, please allow me to do it one more time. XRP means XRP Rate XRP is a token. XRP is a popular crypto in the world. It has been keeping a high position in the ranking of all cryptos. Well, XRP Ledger is a layer 1 blockchain of XRP token. It has another name, Ripple Protocol, which is rarely used in these days. XRP Ledger was created and open sourced by a company named Ripple. Nowadays, Ripple is still making substantial contributions to the codebase of XRPL, and the bug bounty program of XRP is currently maintained by Ripple too. As a layer 1 blockchain protocol, XRP Ledger has the following features: trust lines and rippling, which support for issuing and transferring a non-native currency. Some exchange features that support on-chain token exchanging. And a great feature that it does not support for any kinds of smart contracts, which helps it decrease a great big attack vector. Its consensus algorithm is based on BFT, named the Ripple Protocol consensus algorithm. In this consensus network, there are two types of participants. One is the tracking server, which distributes transactions from clients and responds to queries about the ledger. And the other one is validator. It performs the same functions as tracking servers and also contributes to advancing the ledger history. RippleD is the node server program of XRPL. It's written in C++ with heavy use of Boost and SDL. It's the only server implementation that composes the XRPL network. The C++ implementation attracts me to see if there is any source of memory corruption vulnerabilities in it. So I started to analyze the attack vectors and found that the two main attack vectors are RPC and P2P. Considering that the RPC service is not always open to everyone, I chose to fuzz the P2P protocol. The node P2P communication is accomplished first by a HTTP handshake to exchange the basic information, including a TLS key used to encrypt the following messages, then a protobuf-based P2P communication set up to exchange all information about the chain, like transactions, validations, blocks, pairs, and so on. There are approximately 25 types of P2P message, and each of them has a protobuf style definition. This is so great because we do not even need to write them by ourselves if we're gonna fuzz it with structure-aware fuzzing. So I quickly set up a fuzzer based on the leap fuzzer and add the structure-aware feature and improve it again and again until I found the bug. But before talking about the bug, let me first introduce you the peer finder component, which is where the bug lies in. When a peer comes online, it needs a set of IP addresses to connect to. It first connects to a hard-coded peer as an initial bootstrapping node. It then receives endpoint messages from its connected peers and tries to connect to recommended peers until the connections reach a specific number. Upon receiving endpoint message, a peer will store all the related information into the lab cache, which is in memory. And if the connection to a peer is opened successfully, it will store the related information into the boot cache, which is in the disk, and the information will be used in the following bootstrappings. And the bug was located in the logic of the lab cache component. This insert function is used to add endpoint information into the lab cache. The endpoint contains a hops field, which stands for the network distance between two peers. The lab cache uses the mlist variable to store all the incoming endpoint information, and mlist is an array with fixed length. The type of the array element is a boost list. So the whole thing is like this. It will say that mlist consists of 8 double-linked lists. These lists are used to store endpoints with the corresponding hops. So you may have already know what's going on if you went back to check where these hops come from. You would find a bug. The hops initially comes from an unsigned int field in TM and points, which is a protobuf message. On receiving this message, the peer will transform it into an inner object named endpoint. Badly, the type of hops in endpoint class is signed int, and this is the root cause of the vulnerability. This is not enough. There is not enough verification before or after the transformation. It makes an endpoint with a negative hops can be added directly into the lab cache and causes the mlist array and flowing. Well, there is verification that ensures the hops is not larger than max hops, so the overflow is impossible. That's to say we can only do the OOB write to the memory before mlist. When we got a OOB write vulnerability, we always need to know how the buffer is allocated. And here are all the reference relationships of lab cache. Just from the bottom, we can observe that lab cache is a member of mlogic, and mlogic is a member of peer finder, which is a member of overlay, and the overlay is a member of application implement. The application implement will be allocated only once at the beginning of the program. Thus, the lab cache is the same. It always keeps on same address in the whole lifetime of the repo process. which means it's impossible to put the overflowed buffer into a pre-construct area. But this gives us another feature, that the memory before the overflowed buffer is very stable because these fields all belong to the same big object. Or maybe we could find some useful objects among them. Besides, the last thing we need to check is what is going on when a push front is called. We can find the logic in both codes. It's a set of typical operations of double-linked list. You get the root node, you get the next node, and the prim node, and you set the pointers to point to the exact nodes. Cool. Now we got an array outer bound push vulnerability, and we know that the array is allocated at program initialization, and it won't be freed until the program stops. To exploit the vulnerability, my first instinct is to search for some double-linked lists of the other objects. And maybe I can create a type confusion after inserting an endpoint object to that list. But I found that there was not much list before the overflowed buffer. For the only remaining list, nothing would happen when I insert an endpoint into the list, so it failed. I went back to rethink about the push front operation, and I found that things I could do could be more. Imagine that we have memory like this. The pre-pointer is not pointing to the root node. Instead, it's pointing to another address. As we are doing a push front operation on this root node, it will find the next node according to the next pointer of the root node, and find the prim node according to the pre-pointer of the next node. After that, except for the pointers of endpoint node being set, we now have the pre-pointer of the next node being set. And more importantly, we have the next pointer of the fake prim node being set. In other words, we have the ability of writing a memory after two-pointer dereferences. This ability greatly extends the area we can write. After that, I wrote a HITB script to help me find all the potential addresses that we can perform a memory write after two-pointer dereferences without triggering any segmentation fault. And I got over 20 gadget addresses like this. What encouraged me was that I quickly found a DOS gadget among these addresses. It's a little bit magical that all the things you need to trigger the DOS is just sending an endpoint message with a specific negative hops. And that's the cool part. Among the gadgets, there is a pointer of IO service. IO service is a fundamental object in Boost ASIO library. It's used to access the core asynchronous IO functionality. Inside of IO service, there is another pointer named MMPL, which is pointing to the real underlying implement of IO service. At the time we perform a OOB push front on the IO service gadget address, the IO service object will be treated as next node, and IO service MPL will be treated as prim node. It will change the pre-pointer of the next node, which is the MPL pointer in the I/O service object in this case, that means the whole I/O service MPL object is replaced by a fixed object. The spin lock in the original object won't be released anymore, so it's a deadlock that leads to the DOS. But there is another thread that keeps monitoring the situations where a deadlock happens. It will force shut down the program when it's over 10 minutes after a deadlock is detected. So, one malicious endpoint message will cause the server to hunt for 10 minutes. Although the harm of DOS is already great enough for this kind of decentralized network, a RCE exploit is still a good ending. The RPL process is managed by Linux system D, making it restart automatically after a crash. And considering that the PIE is turned off, it's worth to have a try. After I went through all the collected gadget addresses, I found that some of them could cause a virtual function table hijacking. The vtable pointer would be replaced by the address of the endpoint object to be pushed front. And we would hijack the control overflow if we could trigger a virtual function call to a controlled field. Well, this is the most difficult part. This is what an endpoint looks like in the memory. The IP address field seems to be the only payload holder, but there are still some verifications on the inputted IP addresses, making it more difficult to be used. Creating control overflow hijacking in such a situation was a pain. After a few failures, I decided to give up the use of IP address field and turning to do the heap spraying. Ideally, if the memory adjacent to the endpoint object is controlled by us, we need only to use a longer virtual function call, which we have already got previously, to achieve the control flow hijacking. But it's also not easy. As a contract-free blockchain application, there are only a few interfaces that accept binary bytes as input. The internal objects, which might be created by incoming P2P message, are under strict management. And developers always keep in mind that they should avoid potential DOS vulnerability, as DOS is a really serious issue for blockchain businesses. For example, the endpoint object will be freed in 30 seconds after being created. As for the transaction object, well, there is a condition field which can hold arbitrary bytes. The node server will only store 250 transactions at most, pending to be parsed. And if you are considering to use real valid transactions to do the heap spraying, you should remember that your transactions will be broadcasted to the whole network, which may lead to unpredictable behaviors. And another idea came to my mind when I saw the protobuf definition of the manifest message. The TM manifest message holds only one field, and the type of the field is bytes, which is a variable length array. And the TM manifest message can hold any number of TM manifest. I was curious about how protobuf managed those memory buffers, it seems that the field with a repeated keyword is in type repeated PTR field. According to the documents, these classes are very similar to STL's vector. Okay, that's much easier to understand. It's just like vector. And the field in bias type is internally an object called arena string PTR. The documents say that this class encapsulates a pointer to a STD string with or without arena-owned contents, meaning that the arena string PTR could be pointed to a STD string in some ways. This is important because that only when those buffers come from the same heap as our endpoint object does, can we have the chance of putting them together. So I quickly attached a debugger to the RepoD process and found that the buffers that hold bytes in TM manifest are just normal chunks from the glibc heap. It's the same as endpoint object. Great. Now we have the ability of allocating buffers with controllable continents. But we still cannot keep those buffers in memory for a long time. Once the program found that all of the manifests in our message are invalid, it will free the buffers at once. It's hard to create a valid manifest because a manifest can only be authorized by the validators. Actually, we do not need the manifest to be acceptable. Remember that one TM manifest message can hold an unlimited number of TM manifest messages. And all the TM manifest messages are iterated in this loop without fast building up. According to my tests, a message filled with over 80,000 invalid manifests will make the loop consume 1 or 2 seconds. And I'm gonna finish the exploit in this time window. Common keep string idea that firstly creates holes in memory and then fills the holes with the target is not suitable for this situation, as we cannot do allocation and deallocation on command. So I choose a workaround to help me finish the keep string. At first, I will send 2 manifest messages that is about 64 MB each. The memory layout will be like this. Each message will help me allocate over 80,000 buffers. At the time when the second manifest message is going to be freed, I will send an endpoint message to allocate a buffer for the endpoint object. And then send another 2 manifest message to fill the memory below. This message is less accurate, but it does work. And I finally improved the success rate to about 30%. And this is a success case of heap string. We can see that our payload is just below the endpoint object, and the memory range of the faked vtable is marked as blue. Once the specific virtual function call is called, the control flow will be hijacked, and the LP begins. At last, the arbitrary code execution is achieved. So we all know that as a decentralized system, it means nothing unless you can control most of the nodes. To have a thorough understanding of this vulnerability, I have performed some experiments to estimate how this vulnerability could be exploited in the real world. I have tested the exploit under different network environments, and it turns out that an attacker could leverage this vulnerability to subvert one node server in 12 minutes with a total outgoing network traffic of about 1 GB. And if he attacked the whole XRPL network with only one machine, he would finish the attack in 9 days. Well, he could also use multiple machines to attack in parallel and speed up the process. And one more question is, what would the attackers do to gain profit after compromising the entire network? And here are some brainstorms of mine. Plan A. He steals wallet credentials, which are possibly stored on the compromised servers. Plan B. He steals assets from exchange by controlling their XRPL node servers. Plan C. He gains profit through the double spending attacks. And Plan D, he hijacks some critical logic of all compromised servers, such as altering the logic of transaction verification, which will introduce a super backdoor that allows arbitrary transactions constructed by the attackers to be accepted, even if the transactions are illegal. And altering the logic of balance calculation to steadily increase the balance of a specific address over time. Okay, and that's all the ideas. Be sure to take precautions if you own a server, or run an exchange, or you build blockchains. Now let's get into the demo time. In this video, I will use 4 devices to demonstrate the attack. 2 of them are mobile phones, which are used to show the wallet status of the victim and the attacker. The other 2 devices are laptops. One of them will be used to set up local XRPL network by running 3 node servers separately in 3 different virtual machines. And the other laptop will be used to perform the attack. All right. Well, this is the last slide. And the ending of this story is that the vulnerability was fixed silently without explained description. And thanks for the repo team and my employer. And thank you all. Hope you enjoy this talk.
Thank you very much. Do we have any questions? No further questions? Ah, there you go.
Hi, sorry, I missed the beginnings. Maybe you said it. Did you receive a bug bounty for reporting this bug?
Yeah, there is a bug bounty.
Are you comfortable with sharing what the bug bounty was? I mean, you don't have to, of course.
It's a 15,000.
Okay, thanks.
$15,000.
Anyone else? A question, maybe? No further questions. And thank you very much for your wonderful talk. The next will commence at 12 o'clock.